So we are happy Friday. We are now 4 lectures. What we're going to do today is the last part of our assignment, or our sort of assigning different properties of molecules. So this is where we've got mostly comparison of molecules in these 2D line bond structures. We've got names for these things we've worked through: isomers, conformations, stereoisomers, and now we talked last time about enantiomers and diastereomers. We left off of this problem. We're going to go into a little more detail here. Last thing we're going to talk about today is chiral properties. Briefly, we're going to mention Fisher projections. Now we're going to talk a little bit about Fisher projections, the major sort of strategy for doing these kinds of questions. I have a long pencast online that you guys can go and review. Next week we're going to do substitutions. So the Fisher projection, long part of it, is online. The major thing I wanted to talk about here, though, remember, last time we introduced 2 new funny words. We have enantiomers and diastereomers. In your own words, how would you say they are different from each other? If 2 molecules are enantiomers, what's special versus 2 molecules are diastereomers? Yes? Enantiomers are mirror images. That's a good way to think about it. Remember, your hands, left and right hands, are mirror images to each other. You have a pair of enantiomers. Diastereomers are what? How would you class a diastereomer? A diastereomer is just just any 2 molecules that are stereoisomers to each other. Now, things that are the same and things that are different. Enantiomers and diastereomers are all in that same class of stereoisomers. Same molecular formula, same basic arrangement, nearly the same IUPAC name, right? If they're both alcohols. Here, these are both called what? They're how many carbons in long chain? There are 4. So they are what kind of parent name in longest carbon chain? This is the bute. What kind of functional group, or what's the sort of, what do we put at the end of this name? It's not just a butane, this is a butan. Not just a butanol, it's a butan. There's 2, so it's a diol, right? They are both butane diols of some kind. They're both butane diols with an oxygen on 2 and 3. So they're both 2,3 butane diols. The absolute geometry, R and S, of their asymmetric centers are different. So we left off last time. We identified these. We have an asymmetric center there. You should be able to see that as an S center. Remember, rank your priorities. Start at that center. You go count from highest to lowest. Lowest priority group is your hydrogen, which is currently facing you in this direction. This is an S center. Other is your also an S center. This is an SS molecule on the left. On the right, this is an RR molecule. If you look at these 2 and just were to compare them, first thing you should identify, both have 2 asymmetric centers. You can assign them as R or S. Most importantly, between the 2, because one of them is SS, the other one is RR, they could never be the same molecule, right? If you were to name these 2, one of them is going to come up, if you name these 2, one comes up as the SS butane diol. The other one is the RR butane diol. So based on that, the fact that you can identify and classify the asymmetric centers, since one is SS, one is RR, they are not the same. They cannot be. And more importantly, remember, we said for an enantiomer, what happens to the asymmetric center? If one enantiomer has SS, the other one must have, has to be. They have to change. S must become R, and a good clue here, since both of them are S, both of them are R, these are absolutely enantiomers. If we do this, we've just changed the geometry of one center. Now again, we do that same sort of assignment. First one is S. What's happened here, that second one, is now going to be an R center, having this geometry up. So this is an SR molecule. If we do the same assignment in the other 2, R, and then at the bottom one, S. So here is one of those cases where you should look at this. Basically, your spidey sense should be tingling here. You have 2 molecules. Both of them are still butane diols. They both have 2 asymmetric centers. But most importantly, what you have here is a case where one is SR, the one is RS. Now this could be, it is true, that S could have turned to the R center could have turned to the S center, but in a molecule that has this high degree of symmetry, the top and bottom of the molecule are the same. This is a really, really, really good case, which you may be looking at a meso compound. There may be an internal plane of symmetry in some conformation that you don't see quite here yet. In this molecule, the way you can see this is if we were to pick up this molecule and we said, okay, I could turn it in the plane of the page, or I could flip it like a pancake. That doesn't quite line it up. The reason this becomes more difficult to see in terms of converting one to the other, there is a third dimension which is rolling it front to back. Imagine picking it up and over. In that sort of case, if you did that, the R at the bottom pointing out becomes the R at the top. The S at the top becomes the S at the bottom. Rolling it this way, from your perspective, gives you that geometry. So this is a movie clip that sort of shows that. If I pick up this molecule and just simply flip it end over end, I get the other geometry. That's how I would interconvert these two visually, or shown live via our side cam. This is the first one we were looking at, where these two groups are on the same side when we're presenting it in this geometry. This is a chiral molecule and will have an enantiomer. It will have a mirror image. The other guy, this one here, one up, one down, this is a meso compound. Even though it still has a lot of symmetry, what's different about this is if I were to just flip these end over end like this, and also what we showed last time is by rotating it so that I'm presenting the carbons in the same sort of place. Now what you can see is the mirror plane down the middle of this ring becomes obvious. Taking the other molecule, bending it this way such the carbons are presented, now what's happened is one oxygen is up, one is down. Compared to my meso compound, rotating it back in this bent sort of curve, you can see that now there's a plane of symmetry between the molecule cutting down this point here. Left and right side are the same. And again, how we pick this up, one of the things to watch for when we do this is I walk through the molecule, as one of them is S and one is R, the plane of symmetry cutting through that middle bond is another thing. Think about that, this another way that this center could be inverted. If I had a mirror plane cutting top and bottom in this ring, the S enantiomer, or S asymmetric center at the top, will be reflected as an R asymmetric center in the bottom. Cutting it in between the ring here gives you that sort of property. Visually, the flip I was talking about can be expressed this way. If we take this molecule, this bond here in the middle, and if I were simply rotate it, I do not change the absolute configuration. Just by bending or rotating centers, not breaking them, R centers are still R centers, S are still S. So I'm just trying to highlight here where those colored bonds are. I've just rotated about the red bond in the middle. Now you can see the S and R centers are presented about this point. The mirror plane down the middle of this molecule allows you to see the mesoplane. And remember, a molecule is meso if in any geometry, any conformation, you can create this mirror plane. Just by rotating them out of the way does not change the absolute configuration in any way. Sorry about that. I don't know why my auto move is on. Does that make more sense? And again, once you look at it like this, where the two methyls are bent back, that looks like the cyclohexane ring, or those ring geometries we've done before. When they're constrained, because the ring is in place, it becomes a lot easier to see that there's a plane, because the molecule can't suddenly untwist itself. It's these linear structures where these meso compounds can become more difficult to see. Again, the way that you can do this, the thing you should pay most closely attention to, assign your asymmetric centers as R or S. If one of them is SS, the other one is RR, you have no fear. There could never be a plane of symmetry that you're missing. If they're both the same, like one is SS, one is RR, you are looking at two different enantiomers. They have fully different IUPAC names. These two here, if we were to name them, they are both SR2,3 butane diols. Doesn't matter which way you call them, you're still going to have one is S, one is R between these two centers. Again, your model kit is your absolute savior when you work through this. Any other questions before we move on to properties? Okay. Doing this assignment is important because molecules that are chiral, molecules that are enantiomers, have a very special property about them. Chiral molecules get elevated to this special point. Being able to identify them is important because chiral molecules do things that are only special to chiral molecules. The biggest thing about them is they interact with chiral environments uniquely. It is, in fact, a chiral environment that is necessary to actually discriminate or tell that you're dealing with a chiral molecule. If you look online, YouTube, if anybody's watched a whole bunch of videos, recently there's been a ton talking about the fourth dimension, fifth dimensional beings. Has anybody seen this, or is this just my YouTube channel? I don't know why, but this has been sort of a ton of stuff coming out recently. We apparently have the same algorithm. The point is, if you were a two-dimensional object, you have no idea the third dimension exists, anything about that. This higher dimension of symmetry is invisible to you. You could never perceive it. Same thing with chiral molecules. If a molecule is achiral, it interacts with the world with all achiral properties, doesn't matter. But once a molecule is chiral, has this third dimension, has this property, there's a lock and key fit that matters. This shape allows you to interact with other molecules with a similar shape differently than not. And again, a simple example, your left and right hands are enantiomers, and how one of your enantiomers interacts with somebody else's right hand is very different than left hand to right hand. There's a discrimination that happens there. So just generally, number one, interacting with chiral species will be different. This is important because you are made of chiral molecules. You are a three-dimensional object. So drugs, pharmaceuticals, chiral molecules will treat you differently. Second, polarized light. Polarized light, if anybody had those awesome polarizing sunglasses, you look at your iPhone screen, what happens? Looks really weird, right? Polarized light, what you're doing is you're aligning the plane of the light such that it can be split into two components, circularly polarized left and right. That light coming out of your iPhone screen is polarized. And if you put a chiral molecule on it, only one of them, one enantiomer will interact differently than the other enantiomer. So, as an example, these are your two molecules. If you look at them, you guys should be able to recognize that we have a single asymmetric center right here. So they are enantiomers. One of them is forward, one is back. One is S-limonene, one is R-limonene. From the name, what does it sound like this thing comes from? Limes? These guys are citrus. They have a citrus smell to them. If you look at the two, melting point. The melting point of S-limonene is minus 95 degrees. The melting point of R-limonene, minus 95 degrees. Melting point is not a chiral property. It's talking about how molecules like to sort of melt down, or like how they interact with it themselves. So there's no difference. Melting point of these two enantiomers does not change. Boiling point, 176, 176, identical. Densities, 0.941, 0.941. What this means is normal colligative properties, physical properties like these, do not tell any difference between these two. Funny thing, for some people, S-limonene is different depending on your biology. S-limonene will smell very, very, very much like citrus. This will smell a lot more like this deep sort of lemon kind of smell. So like tangerines and lemon. It's a subtle piece, but people can tell the difference between the two, not because of any of these properties. The boiling point, the melting point, the density, all the physical properties are the same, but how these molecules interact with the receptors, the proteins in your nose, is different. So what happens is a chiral object, you can discriminate between these two. But if you look at these, go put on your hat as a physical process chemist, you have now been tasked with making a bucket of S-limonene. More importantly, your synthesis gave you a mixture of these two. How do you get them apart? Normally when we separate things, what have you done in the lab to separate things for workups? Have you guys done crystallization? One time, yeah. Boiling point, have you guys separated things by distillation? Crucible, maybe. Again, this is usually better in years not affected by the pandemic. The point is, how we separate things traditionally is we look at properties like this and we say, one thing boils easier than the other, I can extract that easier. One thing is more soluble than something else, I can separate the two from each other. We pick physical properties that allow us to define differences. And the problem is, enantiomers have identical physical properties unless they're working with you. So this becomes really, really hard. So what we have to do, and again, where this comes back, this is thalidomide. Thalidomide has How many asymmetric centers? Lots. I would die. Remember, what do you have to have for an asymmetric center? To be an asymmetric center, you must have sp3. What else? 4 different priority groups. It has only one. If you look through this molecule, sp2, 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 these are all garbage. Why is nitrogen useless? Because it's nitrogen, yes. No. This is your only center. Why are these ones never going to be asymmetric centers? 2 hydrogens, yeah. So we have a single asymmetric center, which means we'll have an R and we will have an S. As it turns out, this thalidomide is a sedative. It helps settle your stomach, it helps you sleep, it helps cure morning sickness. This thalidomide will stop the growth of limbs in fetuses. That was terrible. This was one of the largest, worst things that we had ever learned on a mass scale. This was a drug prescribed as the racemate to pregnant women. And as a result of that, we learned some terrible, terrible things because of this. This was, like, again, people knew that, things kind of smell different. But it wasn't important until we start to see things like this. So what this meant is we now needed a way of discriminating one enantiomer from another, proving that what you had was a single enantiomer, not something else, and ways of separating or making them. The biggest one, and what we're going to talk through today in terms of calculation, is what's known as plane polarized light, or what's called a polarimeter. How it works: you take normal light, some source, you take a polarizer, that would be like the lenses on your polarizing glasses, you then, outcoming from that, you have now discriminated or lined up the light. It is now linearly polarized coming through this sample. It then goes through your sample. Your sample is here in this number 5 part. It's a tube where you put your molecule, light shines through it. As light shines through this, plane polarized light that was aligned one way will interact with the chiral molecule, and it will turn. That means that it works like a little lens where it doesn't really change the intensity, it changes the alignment, which means coming out of it, we have another polarizer. So if you guys taken 2 polarizers and you cross them 90 degrees to each other, what happens? Well, it goes dark, right? Basically, what polarizers are doing is it's taking light and it's sieving it out. And if you take another polarizer, cross-polarized, what happens is no more light gets through. The first one sieves out some, the second one knocks out everything else, nothing can make it through. The only way it'll work is if those 2 polarizers are lined up with each other. So if whatever is here in the middle does not change the polarization of light, line up number 1, line up number 2, there's no difference between the 2, there's no rotation. But if something in the middle bends the light as it goes by, that second polarizer, there at 7, we have to rotate it until we can see the light again. It will be blocked if these 2, 3 and 7, do not properly line up. The light will never make it through to your eye. 5 is acting like a rotation, so what we can do now is measure the degree of rotation. How much do I have to rotate number 7 so that I can still see light, because whatever was in 5 bent that light for me. This is a property that is as old as this guy. Does anybody know who he is? Yeah, you don't have to know. This is if you spend way too much time on Wikipedia, you probably do by sight. That's Louis Pasteur. He is my absolute hero. I apologize, some people last class, they got the kind of preliminary speech to this. Louis Pasteur, what is he known for in your guys' mind? The Pasteur pipette, true. What else? Who had milk this morning? Pasteurization? This dude, right? He was the guy that understood a lot of things about vaccines, bacteria. So the biologists like to claim him, but I'm here to make the case that he's a chemist. He was always a chemist, and he just happened to help out those poor biologists. Pasteur was actually a chemist. He was employed by the wine industry. That molecule in the top corner there, does anybody recognize that? This dude here? Is it chiral? What did we just talk about? If both of them are up, and you were to rotate it, yeah, this is chiral. That is 1 enantiomer of what's called tartaric acid. Tartaric acid, this enantiomer of tartaric acid comes from grapes. It helps to make wine taste a very specific way, and the French love their wine. This was really important. And what the wine industry did is they asked Pasteur, look, we want to be able to make tartaric acid in the lab and add it to our wine, cheap wine, make it better. The problem is, people knew that if you took tartaric acid crystallized from grapes and you put it through this light test, tartaric acid from a grape, you could pass light through it and it would rotate light. They knew about this optical rotation phenomena. They had no idea why it happened, but they're like, okay, tartaric acid from something living rotates light. It has a vital essence. If you make tartaric acid in the lab, it does not happen selectively. You end up with both enantiomers. And as a result of that, they both will interact with light, but they act opposite to each other. Each enantiomer fights each other. And if you have a mixture of both, the light going through lab-grade tartaric acid did not move. So people saw this and were like, wait a minute, there's no way that we're going to take that lab stuff that doesn't rotate light and put it into wine barrels because it's going to kill somebody. Something's wrong with that. Even they knew more than the Germans that actually did the thalidomide thing. So. But the point was, this was a problem that they passed at Pasteur and said, can you figure this out? This is important. They'd known about this chiral phenomena. So what he started doing is he started making crystals. You can't see the molecule, but you can see the crystal. And what he noticed is one particular salt he made came out like this. The lab tartaric acid he made came out as these two crystals. And what do you notice about these two? They're mirror images. He was shocked because he looked under the microscope and he's like, whoa, I've got a population where half the crystals look like this and half the crystals look like this. So he got out some tweezers and he started separating them based on left and right. And lo and behold, the pile of crystals that had like this all rotated light exactly like natural tartrate. This one suddenly looked like this. He was able to do a separation to get something that you normally needed grapes to do. The weirder one is he took the other one here and it rotated light the opposite way. So he had this unnatural tartrate. It had the same properties, and this blew everybody's mind because it went against every single canonical understanding of how lab organic chemistry worked. He had proven that molecules were chiral because they interact with light, and more importantly, molecules that are mixtures of different enantiomers will work as a class or all together. Having them purified, he could return this property, this chirality to it. As it so went, this is a bit of history. You recognize that guy in the middle? Hi. This is during my postdoc. So Pasteur, long ago. This guy over here on the left, that's Barry Sharpless. He was my postdoc advisor. I got to join his lab a couple years after he won the Nobel Prize because he came up with a way to make one enantiomer and not another 100%. Pasteur could separate them. Barry had worked out ways. He was part of a team of people that figured out how we can choose to make one enantiomer and not another. This changed everything. And this is only, he got the Nobel Prize 2001. He worked on this stuff sort of 1970 to 1990. This is cutting edge. This is where we are today. And this is absolutely the leading front of it. So I got to work with him. I got to learn how to do these kinds of things. In fact, we actually adapted this. One of the first things I published was a paper going back to tartrate, and we came up with one of the first modern ways of separating enantiomers here in 2015. So we use this now. We learned a lot from this point, and we're now bringing these pieces together. As it turns out, if anybody's interested, this is now up on our YouTube site. This went sort of viral on Twitter a couple days ago. This is from our lab. These are Pasteur's crystals. We reformed them and we've been looking them under optical properties because the super cool thing is if you look at these, some of them are left and some of them are right. You can do that, but what we're doing right now in the lab is we're teaching a machine vision algorithm, an AI, to do that discrimination for us. We're trying to teach an algorithm to be Pasteur. It's not working yet, but it's coming along. But the thing that's super cool about this, the final part to this, and why Pasteur is my hero, these crystals are weird. They form what's called different polymorphs. If the temperature of the crystallization is above 25 degrees, this doesn't happen. The crystals are not left and right-handed. They all play together. You get what's called the racemate. If you take these crystals and you put them together and you cool them at 22 degrees, they separate. That summer when Pasteur did that crystallization, weird summer, it was cooler than average. He did the crystallization, and just by chance, it was cooler overnight. Had the world been going differently, had there not been whatever caused that summer at that point, he would have missed this completely. We would still be in the dark. Pasteur said, chance favors the prepared mind. Have you heard that before? He's the guy that was really popular, and he's the guy as an observational scientist that pushes this. This is my thesis, and this is why I teach the way I teach. I may not know where I'm going, but I always watch what I'm doing. You need to keep your eyes open because there's little tiny pieces. The world is always whispering to you what the heck is going on, and you have to be ready. Pasteur was one of the guys that embodied that better than anybody I've ever seen. Anyway, polarized light. It matters. And anyway, the first thing we have to be able to do is use this thing analytically. So we have to go through and we look at molecules as enantiomers. We class them as either D or L. That stands for dextrorotary or levorotary. What we mean is, and again, what we're classing when we say D or L, we're just saying that enantiomer will rotate light clockwise to the right or counterclockwise to the left. Okay? D and L corresponds only to the direction in which it moves light. It has nothing, and really important here, this has nothing to do with RRS. RRS geometry talks about the absolute CIP notation based on molecular formula, right? That has nothing to do with a physical property like which way light moves. Left and right, D and L, are talking about which of two possible enantiomers you are dealing with. It's a physical property based on the light. R and S talks about a single center, so don't mix up the two. It is true that if you had one enantiomer that was SSSS and that enantiomer rotated light to the right, you know that the RRRR, its enantiomer, must be the L compound. But before we make that measurement, we don't know yet. We have to make this thing to correlate. We know that enantiomers will rotate light equal and opposite directions. That is a fact. Which one, just by looking at it and saying which is left and which is right, we do not know, and it does not come down simply to R and S. So don't get those things confused. Okay? This is one of the things like our measurements, like our rate determinations. We have to make the measurement in order to sort of be able to make something about it. Once we know what that measurement is, we know what to do. Who's seen this one? So this is Samuel L. Jackson, and clearly his enantiomer, Samuel D. Jackson. Oh, come on, that's got to be better. But this is why I grind it down. You have nothing. We could potentially assign pieces of Samuel's face as R or S. Left and right, the enantiomers are simply just their designation as the L and D point, okay? And have you ever seen this one before and didn't get it? Now you're in the joke, ha ha ha. How we do the calculation is something we call a specific rotation. This is the equation for it. You do not need to know this equation off the top of your head. You do not have to use it. What we're saying with specific rotation is we make a measurement, alpha, how much did the light rotate, what angle, and then we have a length, how big the cell was, and x, the concentration of the sample. More stuff will rotate the same light more, and L, bigger cell, means we have a longer path length. This looks like Beer's law, really. What you're saying is, in Beer's law, more stuff and more material, more absorptivity, will give to higher absorbance based on some concentration. But increasing the concentration will change the absorbance. They're proportional. Same kind of thing here. The amount of stuff you have, the concentration, and the path length will determine how much this stuff rotates or bends, your observed value alpha. We use what's called specific rotation, alpha D or alpha DT, because what we're doing there is that's a value like a standardized melting point we can put in a textbook. It doesn't matter what the concentration of some sample is. If we all measure the rotation of sucrose, the rotation of tartrate, the alpha value does not change. If you choose to do your sample of tartrate, you're going to measure at the bench this value at some concentration in your sample, L. I might choose a different concentration with a different L, and I'm going to measure a different alpha. But both of us, because we are normalizing the values to the concentration, the path length, will have the exact same alpha D value. That's usually what's reported. That's what's useful because it's independent of a specific experiment, okay? Point is, again, if you had this and you were given different concentrations, different L's and different alphas, you should be able to calculate other parts of this. But it's just like a Beer's law type calculation. What matters a lot more is deconvoluting it. The way that optical rotation works, one enantiomer will push light, twist it in one direction. That's some magnitude and some direction. And the other enantiomer will do exactly the same twisting in the opposite direction. So they oppose each other. Two different enantiomers will have exactly the same specific rotation. The sign is only different. Magnitude should be the same given the same concentrations of those two systems. So what we can do, though, is going back to tartrate, the Pasteur example, the stuff he made in the lab was a perfect one-to-one mixture of both enantiomers. And when he tries to measure the optical rotation on it, it came out as 0. It's not that something was special about it. What was happening is the R tartrate in that sample would push it one way, and the S tartrate pushes it back the other. And if there's an equal population of both, if the fraction is 1-to-1, then the opposite specific rotations will lead to a 0 observed value, which means if I can observe some value by this formula, I can calculate the ratio of two enantiomers. This became the standard before any other technique to work out if things were pure or not. So what this also means is, again, back to Pasteur's example, he had what we call a racemic mixture. This is a terminology we use for a special mixture of enantiomers. A racemic mixture means it's not that it is achiral, it's a chiral compound. It's a mixture of two chiral compounds in a 1-to-1 ratio. It's this 50-50 ratio between the two. What does that mean about plane polarized light? It has to be what? It's not going to end up rotating. It's not that the compound is not chiral. It is a chiral molecule. It's just that you've got a 50-50 mixture of the two. And again, everybody give me both hands, left and right. In this normal room, we've got, luckily, because no machining accidents, we have a 50-50 mixtures of left and right hands. We have a racemic mixture of hands in this class. Everybody give yourselves a kind of. That's what we determine. A racemic mixture means you have chiral objects, you just have a population made up of 50-50, half of each. So we have these three different designations we use with optical materials. Optically pure means you have a sample that is chiral, that is only a single enantiomer. An optically pure compound will have a rotation that equals either the perfect enantiomer, the measured alpha D value of one enantiomer, or its opposite. The only thing that's different in terms of its magnitude is the sign, right? The only difference between the two enantiomers is the sign between the both. But if it matches what we call a literature value for that sample, we call it optically pure. Optically active is what we use for any sample that's moving light. It's just less than the perfect value. Optically pure might be plus 90 or minus 90. But an optically active sample, mixed of both, might come out as 30, minus 20, something that is less than the pure value. We know it's still moving light, it's just not enough to call it pure. Optically inactive, if something you put light through, it means one of two things. So you do have to go do a little bit more work. If you take a sample, you put a polarizer on it, and it does not move light at all, it's the same, it has a 0 rotation, it means one of two things. Either the sample is made of achiral materials, it's not possible to bend light, or the sample is made of a racemic mixture. It's chiral, there's just a 50-50 mix. So now we have these three different possibilities. If you know the absolute rotation of a pure molecule, you measure it and it matches the optical value, you have an optically pure sample. If you know the rotation of a pure molecule, you measure your sample, it's rotating light, but not equal to our pure, it's active. If you measure this sample, you're pretty sure there should be chiral materials in there, and it comes out as 0, you either have a racemic sample or you messed up, and there's no achiral sample in there at all. So these become our three categories. So let's apply it to a calculation. Here we have carvone. Does anybody know what carvone smells like? Oh yeah, of course. It smells like caraway seeds. Does anybody know what caraway is? It's like black licorice kind of smell, right? Like anise. So our carbone, it smells different than its enantiomer, but our carbone has a specific rotation of minus 70 degrees. So with this information, we've been given a couple big things. This geometry of our carbone has an alpha D value of minus 20. What does that mean the rotation of S carbone must be? If you know our carbone is minus 72, S carbone must be positive 72. Same magnitude, opposite direction. So having this piece of information suddenly clicks the others into place. Okay, we have a sample, we put it through the value, and we measure that that sample has an optical rotation of plus 50.4. What do I call this sample? Optically pure, optically active, or optically inactive? Yeah, this is optically active. It is not optically pure because we're looking for 72 or minus 72. We don't got it. We got 50. It is not optically inactive. It's bending light. So it's something in the middle. Now what we have to do is work out what is the percentage or ratio. If we know the compound is only made up of carbone, it has to be some ratio of the two. One of them is pushing one way, one is pushing back. Just from this number, which is the maximum? Which is more than 50%, R or S? Yeah, if R is rotating minus and you observe that it's plus, you must have more of the positive rotating enantiomer, D or L. A plus rotation means what? We call that D or L. Yeah, dextro, which is good because it's right-handed, D. Levo, which is left, which is evil, is bad, negative. So this is a plus rotation. It means that we've got to have more of the D carbone. Remember, D and L does not immediately correspond to R and S. We have to do that measurement to know. In this case, our carbone happens to rotate light negative. We would call that the L carbone, or L enantiomer. So what we know is there must be more of the S, or the positive rotation here in this molecule. We have to work out what that percentage is. So what the math would look like is like this. The observed rotation is equal to the fraction of our R multiplied by the rotation of the R plus the fraction of our S multiplied by the rotation of the S. Now from what we've talked through, we know that there should be a majority of this S compound here. We know what the observed value here was equal to 50.4 degrees. We also know the rotation of the R was equal to minus 72 degrees. That means the rotation of the S must be plus 72 degrees. The two unknowns we're dealing with are these values. That's the percent of each of them. Now in this case, we have two unknowns, but remember, the sum, the total sample, must equal to the fraction S plus the fraction R. And we can say that's equal to 100% or it equals 1. Whatever point value of each of these must add up to a total of 100% or 1. So what I'm going to do is say, okay, how much S I have, I'm going to call that X. I don't know this, but I can re-express it where the fraction of R can be written as is equal to 1 minus X. So I have one term here that I can sub in for my fraction R, and I've got one term here, X, I can sub in for my fraction S. So this would be X here. This is 1 minus X. So now I've got a complete term with only one unknown. I know my overall rotation. I know the rotation of the two R and S, and I assign that based on the information that was given. That will depend on the compound that you're actually using. Difference here, X, 1 minus X. This is where we have to go through these two pieces. So all we have to do is rearrange this and solve for X. We get, so 50.4 degrees is equal to minus 72 plus 72x plus 72x. Or 144x is equal to 122.4. X is equal to 0.8 0.85. Now with all these calculations, especially if you've done a definition like this, I always go back. What did we call x? X was the fraction of which enantiomer? The S, the major. And that makes sense, right? 0.85, 85%. We're saying 85% should be this positive enantiomer. That fits. We're on the right track. What does that mean that the R has to be? If S is equal to, this is our S, R has to be, yeah, S is just equal, or sorry, S is equal to 0.85, R must equal to 0.15. Or 85% of it is R, 15% of it, sorry, 85% of it is S, 15% R, the major and minor. And that makes sense again. Based on our calculation or the concentration of the two things that were provided, we can go through and do that math written out here. We're just setting the unknowns to these two. I've chosen to let x equal to the major based on the value given here. I know that the R is minus. I know my observed is positive. I've chosen to do this. If you happen to want to go the other way, assign each as like opposite, call the R x and the S 1 plus x, that's totally fine. You'll just end up with these two values. X here would be equal to 15 or 0.15, not 85. When you translate it back over here, just pay attention to what you've defined as your unknown. Any questions on that kind of calculation? It's a proportionate ratio between the two. And again, the most important thing here is you need to be given a single enantiomer and some information about that enantiomer in order to complete the calculation. So what about this? If you have a mixture of R and S, it's measured. Optic rotation is 0. What do you know about this material? You know it was made up of R and S carbone. The optic rotation is 0. How much? What's the percent of R in this sample? Loudly, proudly, we're almost done. This is 50. 50, exactly. It's half. It must be. Is this sample optically active, optically pure, optically inactive? It's optically inactive. Remember, if a sample is optically inactive, there's only two reasons that's possible. There was no chiral molecules there to begin with, or you have a racemic mixture, 50-50 between the two. This is a racemic mixture. What about this? Here's a molecule. We know it's going to rotate light. Is it going to go to the right, to the left, or you can't tell? You have no idea. Anybody picking up and doing R&S on this one? Good for you, great practice, not helpful. If all you're given is a single enantiomer, you know it will rotate light, you have no idea the direction, you have no idea the magnitude, unless you're given other information, okay? It has nothing to do with RS notation of the center. This is a chiral molecule. It has one asymmetric center. We could assign it as R and S. If this one had a rotation, what you see here, if this had a rotation of plus 100, what do we instantly know? The enantiomer must be minus 100. If this is plus 100, all we know is the enantiomer is minus 100. So the two pieces we get from this is a chiral molecule absolutely will rotate light. We do not know which direction or how far. If we know something about one enantiomer, it tells us about the other one. Yes, sorry.
No, I was just going to ask if you could define a chiral molecule as being one that turns light.
Yeah, the definition of a chiral molecule is it will rotate light. That is one of the properties of them. Yes, absolutely. But again, the thing that makes this tricky, if you had a chiral molecule, not a problem. The issue can be you may have a mixture of two chiral molecules. Your observed value may not bang on line up. Yes?
So if you know it rotates like plus 100 degrees, then would it be to the right?
If this rotated plus 100 degrees, yes. Plus means to the right, which means D. Yes, that's correct. Yes?
We're probably just talking about enantiomer. We're not talking about two different chiral molecules.
So, very good point. The statement is, we've been talking about enantiomers, not two different chiral molecules. First, let me reiterate that. If you know something about the sign and direction of one enantiomer, you know with absolute precision the sign and direction of his enantiomer. If this is plus 100, that must be minus 100. But what about this case? Let's say I'm going to put a bromine here, oxygen. Chiral?
Yeah.
Chiral. Will it rotate light?
Yes.
Do I know which way?
No.
But this is chiral. It will rotate light. If I know what this one is, I know his enantiomer. What if in the same mixture I put in this stuff? Is the second molecule chiral?
Yes.
How does it relate to the first one?
It's a different molecule.
Is it an isomer?
No.
Is it a diastereomer?
No.
Is it chiral?
It is chiral.
So what do you think is going to happen to this mixture? Will it rotate light?
Yes.
Probably. If I told you that this one rotated light plus 100, what is this thing going to do? No idea. But the point is, mixtures of chiral molecules, even if they're totally unrelated, will still each do their own thing. We'd need to know what the other one did. We could use the similar calculations before. So a mixture of an enantiomer and an enantiomer will have this perfect opposite sort of push-pull tug-of-war. But an enantiomer, or a single molecule, and its diastereomer, they're both chiral, potentially. They will both push light, but not in this perfect 50-50 mixture. If this was a 50-50 mixture of, let's say, bromine and OH, this one and this one, what's their relationship to each other? Enantiomers? Are they mirror images? Are they both chiral? Yeah, there's no plane of symmetry. No plane of symmetry, you're good, right? Bromine, oxygen, you're good. You're only different at this center. But a 50-50 mixture of this doesn't have to be zero. One's going to push light one way, the other one's his diastereomer. They're chiral, they'll interact, but they're not going to be this perfect opposite. We don't know anything about this one yet. Yes?
So knowing the rotation doesn't tell you nothing about the rotation of diastereomers?
Knowing the rotation tells you nothing about the rotation of diastereomers. Knowing the rotation is a nice crisp high five of like, cool, you know something about one other molecule in the world. Great. So it's awesome and terrible at the same time. If you get really into it, there are some weird calculations you can do. There's some inferred properties. But honestly, a large chunk of what my PhD was, because at that time we really lacked a lot of ways of doing this discrimination, was coming up with really creative ways of turning one molecule into something else I could actually measure to relate the two. It was like playing Hess's Law with the worst person in the world. Or I used to describe it as the worst game of Go Fish in your life. So, okay. The last thing we're going to talk about, mention briefly, as I said, is Fisher projections. Fisher projections are yet one more way, just like Newman projections, just like chair projections, of looking at chiral centers. They matter the most when you're talking about enantiomers, and they're used primarily in biochemistry around sugars. Fisher was a guy that was looking very heavily at the sugar geometries. At the time, he came up with a convention where he said, look, I'm going to take the carbon chain, and I'm going to choose to look at the carbon chain not as a tetrahedron, but for convention, I'm going to look at it like this. So what he was doing is saying, imagine, here's my tetrahedral projection, but instead of drawing it as this tetrahedron, I want to imagine looking down, splitting those two things, the thing that is forward and back, as if they are flanking the sides of your head. So in your head, you imagine looking at this. I'm going to stare at the carbon in the middle. I'm going to put the carboxylic acid straight up on my forehead. I'm going to put the methyl down to the floor. That's the line of three carbons, up and down. That's why they're lined up this way. And they're facing away from you when you do that. That means that the hydrogen and oxygen are flanking either side of your head. They're coming out towards you, and it looks like this bow tie. And even he thought this looks ridiculous, so he draws it like this. So he's collapsing it. The Fisher projections concept is you take what would have been a tetrahedron, you draw it as a cross, where the convention on the cross is things left and right on this cross are pointing out at you. Things top and bottom are pointing away from you. So what that means is it looks like this. I take, let's say these three are in plane, green, black, yellow. Forward is red, back is blue. I take it, I look straight ahead at it. These two are coming out at me. They're side to side. These two, top and bottom. That's what the Fisher projection cross is meant to do. So it's like flattening this part down. Okay, like I said, go check out the Fisher projection video. We'll start on substitution on Monday. Have a great weekend, guys.